Learning objectives. In this chapter, the user will learn the following in detail: making change, principle of optimality, knapsack problem, shortest path, matrix chain multiplication, activity selection problem, DP solution. Activity selection problem, dynamic programming solution. An activity selection is the problem of scheduling a resource among several competing activities. Select the maximum number of non-overlapping activities from a set of n activities. A is a set which contains the elements A1 up to AN, sorted by finish times. Identify easier subproblems to solve. Set A1 has A1, set A2 has the elements A1 and A2, set A3 has the elements A1, A2 and A3. It goes up to AN equals A. Subproblems. Select the max number of non-overlapping activities from AI. Solving for AN solves the original problem. Solving for A1 is easy. If you have optimal solutions S1 up to Si-1 for subproblems on A1 up to AI-1. How to compute Si? The optimal solution for AI either case 1 does not include AI, Si equals Si-1, or case 2 includes AI, Si equals Sk union Ai for some k less than I. Find such Ak that Ak cannot overlap Ai. Identification of subproblems. Recurrence relation for solution of subproblems. Overlapping subproblems sometimes. Identification of a hierarchy or ordering of subproblems. Use of table to store solutions of subproblems. Memoization. Optimal substructure. Problem statement. Given a set S of n activities. Si, start time of an ith activity. Fi, finish time of an ith activity. Find the maximum size set of mutually compatible activities. Compatible activities. Activities I and J are compatible if the half-open internal Si, Fi and Sj, Fj do not overlap. That is, I and J are compatible if Si greater than or equal to Fj and Sj greater than or equal to Fi. Example: weighted job scheduling. Given n jobs where every job is represented by following three elements of it. 1. Start time, 2. Finish time, and 3. Profit or value associated. Find the minimum profit subset of jobs such that no two jobs in the subset overlap. Input: number of jobs n equals 4. Job details: start time, finish time, and profit. Job 1 has 1, 2, and 50. Job 2 has 3, 5, and 20. Job 3 has 6, 19, and 100. Job 4 has 200 and 200. Output: the maximum profit is 250. We can get the maximum profit by scheduling jobs 1 and 4. Note that there is longer schedules possible, jobs 1, 2, and 3. But the profit with this schedule is 20 plus 50 plus 100, which is less than 250. A simple version of this problem is discussed here, where every job has same profit or value. Recursive solution for activity selection problem. First, sort jobs according to finish time. Now apply following recursive process. Here array is array of n jobs. Find maximum profit of array, n, A. If n equals 1, return array of 0. B. Return the maximum of following two profits. 1. Maximum profit by excluding current job, that is, find maximum profit of array, n-1. 2. Maximum profit by including the current job. How to find the profit including current job? The idea is to find the latest job before the current job in sorted array that doesn't conflict with current job array of n-1. Once we find such job, we recur for all jobs till that job and add profit of current job to result. In the above example, job 1 is the latest non-conflicting for job 4 and job 2 is the latest non-conflicting for job 3. Time complexity of the above dynamic programming solution is big O of n square. Note that the above solution can be optimized while using binary search instead of linear search. Weighted job scheduling in big O of n log n time. Memoized version of algorithm takes big O of n log n time. The time complexity of binary search-based solution is big O of n log n. The algorithm is sort the jobs by non-decreasing finish times. For each I from 1 to n, determine the maximum value of the schedule from the subsequence of jobs 0 to I. Do this by comparing the inclusion of job I to the schedule to the exclusion of job I to the schedule and then taking the max. To find the profit with inclusion of job I, need to find the latest job that does not conflict with job I. The idea is to use binary search to find the latest non-conflicting job. Knapsack problem. The 0 or 1 knapsack problem in dynamic programming. Suppose a hiker is about to go on a trek through a rainforest carrying a single knapsack. That she knows the maximum total weight W that she can carry and she has a set of S of n different useful items that she can potentially take with her, such as a folding chair, a tent, and a copy of this book. Let us assume that each item I has an integer weight Wi and a benefit value Bi, which is the utility value that our hiker assigns to item I. Her problem is to optimize the total value of the set T of items that she takes with her without going over the weight limit W. That is, she has the following objective. Maximize summation of I belongs to T Bi subject to summation of I belongs to T Wi less than or equal to capital W. It is an instance of the 0 or 1 knapsack problem and it is called as 0-1 problem because each item must be entirely accepted or rejected. Characterizing subproblems. Easily solve the 0-1 knapsack problem in theta of 2n time by enumerating all subsets of S and selecting the one that has highest total benefit from among all those with total weight not exceeding W. A dynamic programming algorithm for the 0-1 knapsack problem that runs much faster. One of the hardest parts of the designing such an algorithm for the 0-1 knapsack problem is to find a nice characterization for subproblems. To simplify the discussion, number the items in S as 1 to n and define for each k belongs to the set 1 to n. The subset Sk contains items in S labeled 1, 2 and it goes up to k. One possibility is for us to define subproblems by using a parameter k, so that subproblem k is the best way to fill the knapsack using only items from the set Sk. This is a valid subproblem definition. How to define an optimal solution for index k in terms of optimal subproblem solutions. Derive an equation that takes the best solution using items from Sk-1 and considers how to add the item k to that. If we use this characterization for subproblems, then an optimal solution to the global problem may actually contain a suboptimal subproblem. This figure showing that the first approach to defining a knapsack subproblem does not work. The set S consists of 5 items denoted by the weight benefit pairs 3, 2, 5, 4, 8, 5, 4, 3 and 10, 9. The maximum total weight is W is equals 20. A. Best solution with the first 4 items is shown in this figure. B. Best solution with the first 5 items, we shared each item in proportion to its benefit, is shown in this figure. A better subproblem characterization. Defining subproblems only in terms of an index k is fatally flawed is that there is not enough information represented in a subproblem to provide much help for solving the global optimization problem. We can correct this difficulty by adding a second parameter w. Formulate each subproblem as that of computing b of k, w, which is defined as the maximum total value of a subset of sk from among all those subsets having total weight exactly w. b of 0, w equals 0 for each w less than or equal to capital W, and derive the following relationship for the general case. b of k, w equals b of k minus 1, w if wk greater than w. Max of b of k minus 1, w, b of k minus 1, w minus wk plus bk else. That is, the best subset of sk that has total weight w is either the best subset of sk minus 1 that has total weight w or the best subset of sk minus 1 that has total weight w minus wk plus the item k. Since the best subset of sk that has total weight w must either contain item k or not, one of these two choices must be the right choice. Thus, we have a subproblem definition that is simple. It involves just two parameters k and w and satisfies the subproblem optimization condition. Moreover, it has subproblem overlap. For the optimal way of summing exactly w to weight may be used by many future subproblems. In deriving an algorithm from this definition, we can make one additional observation, namely that the definition of b of k, w is built from b of k minus 1, w and possibly b of k minus 1, w minus wk. Thus, we can implement this algorithm using only a single array b, which we update in each of a series of iterations indexed by a parameter k, so that at the end of each iteration, b of w equals b of k, w. Idea of developing a dynamic programming DP algorithm for knapsack problem. Step 1. Structure. Characterize the structure of an optimal solution. Decompose the problem into smaller problems and find a relation between the structure of the optimal solution for the original problem and the solutions for the smaller problems. Step 2. Principle of optimality. Recursively define the value of an optimal solution. Express the solution of the original problem in terms of optimal solutions for smaller problems. Step 3. Bottom-up computation. Compute the value of an optimal solution in a bottom-up fashion by using a table structure. Step 4. Construction of optimal solution. Construct an optimal solution from computed information. Step 3 and 4 may often be combined. This figure shows dynamic programming algorithm for solving the 0-1 knapsack problem. Analyzing the 0-1 knapsack dynamic programming algorithm. The running time of the 0 or 1 knapsack algorithm is dominated by the two nested for loops, where the outer one iterates n times and the inner one iterates at most capital W times. After it completes, we can find the optimal value by locating the value b of w that is greatest among all w less than or equal to capital W. Making change. Dynamic programming technique is used primarily for optimization problems to find the best way of doing something. Brute force search for the best is computationally infeasible for all but the smallest problem sizes. Dynamic programming is a bottom-up technique. Bottom-up means start with the smallest subproblems, combining their solutions, obtain the solutions to subproblems of increasing size until arrive at the solution of the original problem. However, if the problem has a certain amount of structure that we can exploit. This structure involves the following three components. 1. Simple subproblems. There has to be some way of breaking the global optimization problem into sub-problems, each having a similar structure to the original problem. Moreover, there should be a simple way of defining sub-problems with just a few indices like I, j, k, and so on. 2. Sub-problem optimality. An optimal solution to the global problem must be a composition of optimal sub-problem solutions using a combining operation. Should not be able to find a globally optimal solution that contains suboptimal sub-problems. Then 3. Sub-problem overlap. Optimal solutions to unrelated sub-problems can contain sub-problems in common. Such overlap improves the efficiency of a dynamic programming algorithm that stores solutions to sub-problems. Now that we have given the general components of a dynamic programming algorithm. Dynamic programming solution to the coin changing problem. Consider the problem of making change for n cents using the fewest number of coins. Assume that each coin's value is an integer. What can we do? To make change for n cents, going to figure out how to make change for every value x less than n first. Then build up the solution out of the solution for smaller values. Concentrate on computing the number of coins. Later, recreate the solution. Let C of P be the minimum number of coins needed to make change for P cents. Let X be the value of the first coin used in the optimal solution. Then C of P equals 1 plus C of P minus X. Characterize the structure of an optimal solution. The coin changing problem exhibits optimal substructure in the following manner. Consider any optimal solution to make change for n cents using coins of denominations d1, d2 up to dk. Now consider breaking that solution into two different pieces along any coin boundary. Suppose that the left half of the solution amounts to b cents and the right half of the solution amounts to n minus b cents, as shown in this figure. Climb 1. The left half of the solution must be an optimal way to make change for b cents using coins of denominations d1, d2 up to dk, and the right half of the solution must be an optimal way to make change for n minus b cents using coins of denominations d1, d2 up to dk. Proof. By contradiction, suppose that there was a better solution to making change for b cents than the left half of this optimal solution, as shown. Then the left half of the optimal solution would be replaced with this better solution, yielding a valid solution to make change for n cents with fewer coins than the solution being considered. But this contradicts the supposed optimality of the given solution. An identical argument applies to the right half of the solution. Thus, the optimal solution to the coin changing problem is composed of optimal solutions to smaller sub-problems. Recursively define the value of the optimal solution. First, we define in English the quantity we shall later define recursively. Let C of P be the minimum number of coins of denominations d1, d2 up to dk needed to make change for P cents. In the optimal solution to making change for P cents, there must exist some first coin di where di less than or equal to p. Furthermore, the remaining coins in the optimal solution must themselves be the optimal solution to making change for p minus di cents, since coin changing exhibits optimal substructure as proven. Thus, if di is the first coin in the optimal solution to making change for p cents, then C of p equals 1 plus C of p minus di, that is 1 di coin plus C of p minus di coins to optimally make change for p minus di cents. We don't know which coin di is the first coin in the optimal solution to making change for p cents. However, we may check all k such possibilities subject to the constraint that di less than or equal to p and the value of the optimal solution must correspond to the minimum value of 1 plus C of P minus Di by definition. Furthermore, when making change for 0 cents, the value of the optimal solution is clearly 0 coins. We thus have the following recurrence, which is in claim 2. Claim 2 is shown in this figure. Proof. The correctness of this recursive definition is embodied in the paragraph which precedes it. Compute the value of the optimal solution bottom up. Consider the following piece of pseudocode shown in this figure, where D is the array of denomination values, K is the number of denominations, and N is the amount for which change is to be made. Claim 3. When the above procedure terminates for all 0 less than or equal to P less than or equal to N, C of P will contain the correct minimum number of coins needed to make change for P cents, and S of P will contain the index of the first coin in an optimal solution to making change for P cents. Proof. The correctness of this procedure is based on the fact that it correctly implements the recursive definition. The base case is properly handled in line 1 and the recursive case is properly handled in line 2 to 10 as shown in this figure. Note that since the loop defined in line 2 goes from 1 to n, and since di greater than or equal to 1 for all I, no array element C of dot is accessed in either line 6 or 7 before it has been computed. Line 3 to 7 in this procedure is correctly compute min I, that is di less than or equal to P of 1 plus C of P minus di, and C of P is set to this value in line 9. Similarly, line 3 to 8 correctly compute argument min I di less than or equal to P of 1 plus C of P minus di, and S of P is set to this value in line 10. Construct the optimal solution from the computed information. Consider the following piece of pseudocode which is shown here, where S is the array computed, D is the array of denomination values, and N is the amount for which change is to be made. Claim 4. This procedure correctly outputs an optimal set of coins for making change for n cents. Proof. By claim 3, S of n will contain the index of the first coin in an optimal solution to making change for n cents, and this coin is printed in line 2 during the first pass through the while loop. Since our problem exhibits optimal substructure by claim 1, it must be the case that the solutions to the remaining n minus d of S of n cents be optimal as well. By setting n gets n minus d of S of n in line 3, the first coin in such a solution will be printed in the next pass through the while loop, and so on. Running time and space requirements. The change procedure runs in theta of nk due to the nested loops lines 2 and 4, and it uses theta of n additional space in the form of the C dot and S dot arrays. The make change procedure runs in time big O of n, since the parameter n is reduced by at least 1, the minimum coin denomination value in each pass through the while loop. It uses no additional space beyond the inputs given. Thus, the total running time is theta of nk and the total space requirement is theta of n. Coin changing problem example. To make change for 63 cents using the smallest number of coins. For the following examples, we will assume coins in the following denominations: 1 cent, 5 cents, 10 cents, 21 cents, 25 cents. We will use 63 cents as our goal. We can reduce the problem recursively by choosing the first coin and solving for the amount that is left. For 63 cents, 1 cent coin plus the best solution for 62 cents. 1 5-cent coin plus the best solution for 58 cents. 1 10-cent coin plus the best solution for 53 cents. 1 21-cent coin plus the best solution for 42 cents. 1 25-cent coin plus the best solution for 38 cents. Choose the best solution from among the 5 given above. Instead of solving 62 recursive problems, we solve 5. This is still a very expensive algorithm. Matrix chain multiplication. Dynamic programming is an algorithm that solves the problem of matrix chain multiplication. A sequence chain A1, A2 up to AN of n matrices are given to be multiplied and compute the product. Using the standard algorithm for multiplying pairs of matrices as a subroutine, once we have parenthesized it to resolve all ambiguities in how the matrices are multiplied together. Matrix multiplication is associative, and so all parenthesizations yield the same product. A product of matrices is fully parenthesized if it is either a single matrix or the product of two fully parenthesized matrix products surrounded by parentheses. For example, if the chain of matrices is A1, A2, A3 and A4, we can fully parenthesize the product A1 to A4 in 5 distinct ways, which is shown here. How we parenthesize a chain of matrices can have a dramatic impact on the cost of evaluating the product. Consider first the cost of multiplying two matrices. The standard algorithm is given by the following pseudocode, which generalizes the square matrix multiply procedure. The attributes rows and columns are the numbers of rows and columns in a matrix, as shown in this figure. We can multiply two matrices A and B only if they are compatible. The number of columns of A must equal the number of rows of B. If A is a P by Q matrix and B is a Q by R matrix, the resulting matrix C is a P by R matrix. The time to compute C is dominated by the number of scalar multiplications in line 8, which is P, Q, R. Express costs in terms of the number of scalar multiplications. To illustrate the different costs incurred by different parenthesizations of a matrix product, consider the problem of a chain A1, A2 and A3 of 3 matrices. Suppose that the dimensions of the matrices are 10 by 100, 100 by 5 and 5 by 50 respectively. If we multiply according to the parenthesization A1, A2 and A3, we perform 10 into 100 into 5 equals 5000 scalar multiplications to compute 10 by 5 matrix product A1, A2 plus another 10 into 5 into 50 equals 2500 scalar multiplications to multiply this matrix by A3 for a total of 7500 scalar multiplications. If instead we multiply according to the parenthesization A1 into A2, A3, we perform 100 into 5 into 50 equals 25,000 scalar multiplications to compute the 100 by 50 matrix product A2, A3 plus another 10 into 100 into 50 equals 50,000 scalar multiplications to multiply A1 by this matrix for a total of 75,000 scalar multiplications. Thus, computing the product according to the first parenthesization is 10 times faster. We state the matrix chain multiplication problem as follows. Given a chain A1 to AN of n matrices, where for I equals 1, 2 up to n, matrix AI has dimension Pi-1 by Pi. Fully parenthesize the product A1 up to AN in a way that minimizes the number of scalar multiplications. Note that in the matrix chain multiplication problem, we are not actually multiplying matrices. Our goal is only to determine an order for multiplying matrices that has the lowest cost. Typically, the time invested in determining this optimal order is more than paid for by the time saved later on when actually performing the matrix multiplication. such as performing only 7,500 scalar multiplications instead of 75,000. Counting the number of parenthesizations. Denote the number of alternative parenthesizations of a sequence of n matrices by P of n. When n equals 1, we have just one matrix and therefore only one way to fully parenthesize the matrix product. When n greater than or equals 2, a fully parenthesized matrix product is the product of two fully parenthesized matrix subproducts, and the split between the two subproducts may occur between the kth and k plus 1 matrices for any k equals 1, 2 up to n minus 1. Thus, we obtain the recurrence P of n equals 1 if n equals 1. Summation k equal to 1 to n minus 1 P of k, P of n minus k. If n greater than or equal to 2, applying dynamic programming. Use dynamic programming method to determine how to optimally parenthesize a matrix chain. Follow the 4-step sequence. 1. Characterize the structure of an optimal solution. 2. Recursively define the value of an optimal solution. 3. Compute the value of an optimal solution. 4. Construct an optimal solution from computed information. We shall go through these steps in order, demonstrating clearly how we apply each step to the problem. Step 1. The structure of an optimal parenthesization. This is the first step in the dynamic programming paradigm. Find the optimal substructure and then use it to construct an optimal solution to the problem from optimal solutions to subproblems. In the matrix chain multiplication problem, we can perform this step as follows. For convenience, let us adopt the notation ai to j, where I less than or equal to j. For the matrix that results from evaluating the product ai plus 1, it goes up to aj. Observe that if the problem is non-trivial, that is I less than j, then to parenthesize the product ai plus 1, it goes up to aj. Split the product between ak and ak plus 1 for some integer k in the range I less than or equal to k less than j. That is, for some value of k, we first compute the matrices ai up to k and ak plus 1 up to j and then multiply them together to produce the final product ai up to j. The cost of parenthesizing this way is the cost of computing the matrix ai to k plus the cost of computing ak plus 1 to j plus the cost of multiplying them together. The optimal substructure of this problem is as follows. Suppose that to optimally parenthesize ai plus 1 up to aj, we split the product between ak and ak plus 1. Then parenthesize the prefix subchain ai plus 1 up to ak. Within this optimal parenthesization of ai plus 1 up to aj must be an optimal parenthesization of ai plus 1 up to ak. Why? If there were a less costly way to parenthesize ai plus 1 up to ak, then we would substitute the parenthesization in the optimal parenthesization of ai plus 1 up to aj to produce another way to parenthesize ai plus 1 up to aj whose cost was lower than the optimum, a contradiction. A similar observation holds for how we parenthesize the subchain ak plus 1, ak plus 2 up to aj in the optimal parenthesization of ai plus 1 up to aj. It must be an optimal parenthesization of ak plus 1, ak plus 2 up to aj. Use optimal substructure to show that we can construct an optimal solution to the problem from optimal solution to subproblems. Any solution to a non-trivial instance of the matrix chain multiplication problem requires us to split the product, and that any optimal solution contains within it optimal solutions to subproblem instances. Thus, we can build an optimal solution to an instance of the matrix chain multiplication problem by splitting the problem into two subproblems, optimally parenthesizing ai plus 1 up to ak and ak plus 1, ak plus 2 up to aj, finding optimal solutions to subproblem instances and then combining these optimal subproblem solutions. ensure that when we search for the correct place to split the product, we have considered all possible places so that we are sure of having examined the optimal one. Step 2. A recursive solution. Next, we define the cost of an optimal solution recursively in terms of the optimal solutions to subproblems. For the matrix chain multiplication problem, we pick as our subproblem the problems of determining the minimum cost of parenthesizing ai plus 1 up to aj for 1 less than or equal to I less than or equal to j less than or equal to n. Let m of I, j be the minimum number of scalar multiplications needed to compute the matrix ai to j. For the full problem, the lowest cost way to compute a1 to n would thus be m of 1, n. We can define m of I, j recursively as follows. If I equals j, the problem is trivial. The chain consists of just one matrix ai to I equals ai, so that no scalar multiplications are necessary to compute the product. Thus, m of I equals 0 for I equals 1, 2 up to n. To compute m of I, j when I less than j, we take advantage of the structure of an optimal solution from step 1. Let us assume that to optimally parenthesize, we split the product ai plus 1 up to aj between ak and ak plus 1, where I less than or equal to k less than j. Then m of I, j equals the minimum cost for computing the subproducts ai to k and ak plus 1 up to I plus the cost of multiplying these two matrices together. Recalling that each matrix ai is pi minus 1 by pi, we see that computing the matrix product ai to k and ak plus 1 up to j takes pi minus 1 pk pj scalar multiplications. Thus, we obtain as shown here. This recursive equation assumes that we know the value of k, which we do not. There are only j minus I possible values for k, however, namely k equals I, I plus 1. It goes up to j minus 1. Since the optimal parenthesization must use one of these values for k, we need only check them all to find the best. Thus, our recursive definition for the minimum cost of parenthesizing the product ai plus 1 goes up to aj becomes m of I, j equals 0 if I equals j. Min I less than or equal to k, which is less than j, m of I, k plus m of k plus 1, j plus pi minus 1 pk pj if I less than j. The m of I, j values give the costs of optimal solutions to subproblems, but they do not provide all the information we need to construct an optimal solution. To help us do so, we define s of I, j to be a value of k at which we split the product ai plus 1 up to aj in an optimal parenthesization. That is, s of I, j equals a value k such that m of I, j equals m of I, k plus m of k plus 1, j plus pi minus 1 into pk into pj. Step 3. Computing the optimal costs. At this point, we could easily write a recursive algorithm based on recurrence, which is shown in this figure. To compute the minimum cost m of 1, n for multiplying a1, a2 up to an. This recursive algorithm takes exponential time, which is no better than the brute force method of checking each way of parenthesizing the product. Observe that we have relatively few distinct subproblems, one subproblem for each choice of I and j satisfying 1 less than or equal to I less than or equal to j, which is less than or equal to n, or nc2 plus n equals theta of n square in all. A recursive algorithm may encounter each subproblem many times in different branches of its recursion tree. This property of overlapping subproblems is the second hallmark of when dynamic programming applies, the first hallmark being optimal substructure. Compute the optimal cost by using a tabular bottom-up approach. Implement a tabular bottom-up method in the procedure matrix chain order, which is shown in this figure. This procedure assumes that matrix AI has dimensions pi minus 1 by pi for I equals 1, 2 up to n. Its input is a sequence p equals p0, p1 up to pn, where p dot length equals n plus 1. The procedure uses an auxiliary table m of 1 to n, 1 to n for storing the m of I, j costs, and another auxiliary table s of 1 to n minus 1, 2 to n that records which index of k achieved the optimal cost in computing m of I, j. We shall use the table S to construct an optimal solution. In order to implement the bottom-up approach, we must determine which entries of the table are referred to when computing m of I, j. The previous recurrence shows that the cost m I, j of computing a matrix chain product of j minus I plus 1 matrices depends only on the costs of computing matrix chain products of fewer than j minus I plus 1 matrices. That is, for k equals I, I plus 1 up to j minus 1, the matrix A I to k is a product of k minus I plus 1, which is less than j minus I plus 1 matrices, and the matrix A k plus 1 up to j is a product of j minus k less than j minus I plus 1 matrices. Thus, the algorithm should fill in the table M in a manner that corresponds to solving the parenthesization problem on matrix chains of increasing length. For the subproblem of optimally parenthesizing the chain AI plus 1, it goes up to AJ, we consider the subproblem size to be the length j minus I plus 1 of the chain. The M table computed by matrix chain order for n equals 6 is shown in this figure. The S table computed by matrix chain order for n equals 6 is shown in this figure. The matrix dimensions of the above figure shown in this table. The tables are rotated so that the main diagonal runs horizontally. The M table uses only the main diagonal and the upper triangle, and the S table uses only the upper triangle. The minimum number of scalar multiplications to multiply the 6 matrices is m of 1, 6 equals 15, 125. Of the darker entries, the pairs that have the same shading are taken together in line 10 when computing as shown here. The algorithm computes m of I equals 0 for I equals 1, 2 goes up to n, the minimum costs for chains of length 1 in lines 3 and 4. Compute m of I plus 1 for I equals 1, 2 up to n minus 1. The minimum costs for chains of length L equals 2 during the first execution of the for loop in lines 5 to 13. The second time through the loop, it computes m of I plus 2 for I equals 1, 2 up to n minus 2, the minimum cost for chains of length L equals 3, and so forth. At each step, the m of I, j cost computed in lines 10 to 13 depends only on table entries m of I, k and m of k plus 1, j already computed. The above figures of matrix chain order illustrates this procedure on a chain of n equals 6 matrices. Since we have defined m of I, j only for I less than or equals j, only the portion of the table m strictly above the main diagonal is used. This figure shows the table rotated to make the main diagonal run horizontally. The matrix chain is listed along the bottom. Using this layout, we can find the minimum cost m of I, j for multiplying a subchain AI plus 1 up to aj of matrices at the intersection of lines running northeast from AI and northwest from aj. Each horizontal row in the table contains the entries for matrix chains of the same length. Matrix chain order computes the rows from bottom to top and from left to right within each row. It computes each entry m of I, j using the products pi minus 1 pk into pj for k equals I plus 1 up to j minus 1 and all entries southwest and southeast from m of I, j. A simple inspection of the nested loop structure of matrix chain order yields a running time of big O of n cube for the algorithm. The loops are nested 3 deep and each loop index L, I and K takes on at most n1 values. The algorithm requires theta of n square space to store the m and s tables. Thus, matrix chain order is much more efficient than the exponential time method of enumerating all possible parenthesizations and checking each one. Step 4. Constructing an optimal solution. Although matrix chain order determines the optimal number of scalar multiplications needed to compute a matrix chain product, it does not directly show how to multiply the matrices. The table S of 1 to n minus 1, 2 to n gives us the information we need to do so. Each entry S of I, j records a value of k such that an optimal parenthesization of ai plus 1 up to aj splits the product between ak and ak plus 1. Thus, we know that the final matrix multiplication in computing a1 up to n optimally is a1 up to s of 1, n, as 1, n plus 1 up to n. The following recursive procedure prints an optimal parenthesization of ai plus 1 up to aj given the S table computed by matrix chain order and the indices I and j. The initial call print optimal parents of s, 1, n prints an optimal parenthesization of a1, a2 up to an. The print optimal parenthesization procedure is shown in this figure. From this figure of matrix chain order, the call print optimal parenthesization s, 1, 6 prints the parenthesization a1 multiplied by a2 and a3, a4, a5 multiplied by a6. Principle of optimality. Dynamic programming is a technique for finding an optimal solution. The dynamic programming relies on a principle of optimality. Principle of optimality applies if the optimal solution to a problem always contains optimal solutions to all sub-problems. Principle of optimality applies to multi-stage decision-making problems. A large number of optimization problems satisfies this principle. It applies to a problem, not an algorithm. For example, in matrix chain multiplication problem, not only the value, all the other entries in the table are also represent optimal. This principle can be related as follows. The optimal solution to a problem is a combination of optimal solution to some of its subproblems. The difficulty in turning the principle of optimality into an algorithm is that it is not usually obvious which subproblems are relevant to the problem under consideration. Now the question is how to characterize the space of subproblems. Keep the space as simple as possible. Expand it as necessary. Example. Consider the assembly line scheduling. In this problem, space of subproblem was fastest way from factory entry through stations S1j and S2j. Clearly, no need to try a more general space of subproblems on the hand in case of optimal binary search trees. Suppose we had tried to constrain space of subproblems to subtrees with keys k1, k2 up to kj. An optimal BST would have root kr for some 1 less than or equal to r less than or equal to j. Get subproblems k1 to kr minus 1 and kr plus 1 to kj. Unless we would guarantee that r equals j, so that subproblem with kr plus 1 to kj is empty, then this subproblem is not of the form k1, k2 to kj. Thus, needed to allow the subproblems to vary at both ends, that is, allow both I and j to vary. Shortest path. Let G equals n, a be a directed graph or digraph. N is the set of nodes and a is the set of edges. Each edge has an associated non-negative length. Calculate the length of the shortest path between each pair of nodes. As before, Suppose that the nodes of G are numbered from 1 to n. Capital N equals 1 up to n, and that a matrix L gives the length of each edge with L of I equals 0. L of I, j greater than or equals 0. If I not equal to j and L of I, j equals infinity if the edge of I, j does not exist. The principle of optimality applies if k is a node on the shortest path from I to j. Then that part of the path from I to k and that from k to j must also be optimal. Construct a matrix D that gives the length of the shortest path between each pair of nodes. The algorithm initializes D to L. It then does n iterations. After iteration k, D gives the length of the shortest paths that only use nodes in 1 up to k as intermediate nodes. After n iterations, we therefore obtain the result we want. At iteration k, the algorithm has to check for each pair of nodes I, j whether or not there exists a path passing through node k that is better than the present optimal path passing only through nodes in 1 to k minus 1. Let dk be the matrix D after the kth iteration. The necessary check can be written as dk of I, j equals min of dk minus 1 of I, j, dk minus 1 I, k plus dk minus 1 k, j, where we make use of the principle of optimality to compute the length of the shortest path passing through k. We have also implicitly made use of the fact that an optimal path through k does not visit k twice. At the kth iteration, the values in the kth row and the kth column of D do not change, since d of k, k is always 0. It is therefore not necessary to protect these values when updating D. This allows us to get away with using only a two-dimensional matrix D, whereas at first sight a matrix n by n by 2 or even n by n seems necessary. This figure shows the dynamic programming algorithm for shortest path, that is Floyd's algorithm. It is obvious that this algorithm takes a time in theta of n cube. In this case, we have to apply the algorithm n times, each time choosing a different node as the source. If we use the version of Dexter's algorithm that works with a matrix of distances, the total computation time is in n by theta of n square, that is in theta of n cube. The order is the same as for Floyd's algorithm, but the simplicity of Floyd's algorithm means that it will probably be faster in practice. In this case, we use the second matrix P initialized to 0. The innermost loop of the algorithm becomes as follows. The example of Floyd's algorithm is shown in this figure. When the algorithm stops, P of I, j contains the number of the last iteration that caused a change in D of I, j. To recover the shortest path from I to j, look at P of I, j. If P of I, j equals 0, the shortest path is directly along the edge I, j. Otherwise, if P of I, j equals k, the shortest path from I to j passes through k. Look recursively at P of I, k and P of k, j to find any other intermediate nodes along the shortest path. For example, consider a digraph G equals V, A with non-negative arc distance Cij, which is shown in this figure. Here, the given problem is to find the shortest path from S source to T destination. Naive approach. Find all paths from S to T. Evaluate the length of each S to T path. Find the minimum length. The number of S to T paths increases exponentially, infeasible for large graph. Observation. If the S to T shortest path passes by node P, the subpaths S, P and P, T are shortest path from S to P and from P to T respectively. D of V equals length of shortest path from S to V. Then D of V equals min I belongs to capital V minus small v d of I plus civ. For I not equals s, the complexity of calculating d of v is big O of m. Suppose modulus of v equals n and modulus of a equals m. Order the nodes such that I less than j for all I, j belongs to a. dk of j, length of shortest path from s to j, containing at most k arcs. Then dk of j equals min of dk minus 1j, min I belongs to v minus j, dk minus 1 of I plus cij. Increasing k from 1 to n minus 1, we obtain the shortest path. Complexity of the algorithm is big O of mn. Conclusion. In this chapter, we have covered the following in detail: making change, principle of optimality, knapsack problem, shortest path, matrix chain multiplication, activity selection problem, DP solution.